Okay, and here we go. We're starting Chapter 3, Section 1. In Chapter 3, Section 1, we're going to cover measures of center. You may have seen some of these terms before, so mean, mode, median, things like that. And then in the next part of the chapter, we'll get into variation and standard deviation. And then we'll go into Chapter 3.3, where we'll cover relative standing and box plots. Okay, so to start out with 3.1, key concepts. The focus of 3.1 is going to be to obtain a value that measures the center of a data set. We'll cover 4 common measures of center. In particular, we'll go through mean and median. The objective will be not to only find the value of each measure of center, but also to interpret what those values mean and what we can actually say from that measure of center. What does that really mean? Okay, so first, to define a measure of center is a value at the center or middle of a data set. Within measures of center, we'll focus on mean, median, mode, and mid-range. The first one we'll cover is mean. So the mean of a data set is the measure of center found by adding all of the data values and dividing by the total number of data values. Now you might be thinking to yourself, isn't this just the average? Well, I have a special note on this. So classically, statisticians say mean and they never say average. And because we're all statisticians now, we're becoming them, we're not going to say average either. We're going to say mean. So to caution you against using the term average, never use the term average when referring to a measure of center. The word average is often used for the mean, but it's sometimes used for other measures of center. We need to be specific. So rather than saying average, we should specify mean or whatever measure of center we're talking about. And here's this sort of funny little cartoon related to this concept of mean versus average. So again, the term average is not typically used by statisticians, and we all are statisticians now. It's also not used in the statistics community or in professional journals that may report mean values. Okay, so the takeaway here, we're going to call it mean and not average. Let's get into some properties of the mean. Sample means drawn from the same population tend to vary less than other measures of center. And once we get more into other measures of center, this will make more sense. The second property, the mean of a data set uses every data value in the data set. Okay, and again, this will make more sense as we talk about how to calculate the other measures of center in this chapter. A disadvantage of the mean is that just one extreme value, which we call an outlier, can change the value of the mean substantially. Now, another set of terminology you'll hear in this section is this idea of resistance. So a statistic is resistant if the presence of an extreme value, like an outlier, does not cause it to change very much. Okay, so essentially, if we can include some extreme value and it doesn't change that measurement, then that statistic is resistant. For means, however, if we add in some extreme value, that extreme value or outlier will impact the mean. So this is why we say the mean is not resistant. Now let's go through some notations and symbols. This is sigma. It denotes the sum of a set of data values. So sigma or sum, summation. Next, we have x. This is the variable usually used to represent the individual data values. Now you've seen n before. This represents the number of data values in a sample. Whereas capital N, this represents the number of data values in a whole population. And if you need to go back to chapter 1 to refresh yourself on sample versus population, go ahead and make a note to do that now. Okay, another symbol here is x with a line over it. We call this x bar, and it's the mean of a set of sample values. And recall the difference now again between sample versus population. Now here we have this Greek symbol. It's pronounced mu. And it's the mean of all values in a population. Okay, so again, really importantly to go back and remember what sample versus population means. Another thing I want to point out here is that when we're calculating x bar, or the mean of a set of sample values, we use lowercase n because lowercase n represents the number of data values just in the sample. Now here we go back to mu, and here you see capital N in the denominator, because this represents the number of data values in the whole population. Okay, so that's some important terminology to keep in mind as we go through the rest of this section. Let's do an example. So for data set 32, it's in the appendix of your textbook, and it includes measures of data speeds of smartphones from different carriers. Okay, so here's our question. Find the mean of the first 5 data speeds for Verizon. So 38.5, 55.6, 22.4, 14.1, and 23.1. It is important to verify here that all of these data values are in the same unit. And in this case, they're all in megabits per second, or Mbps. Okay, so feel free to pause this, calculate the mean, and then press play. Now let's go to the solution. So here's our question. To set this problem up, we first want to realize that we want to use the x bar and lowercase n in our equation, because here we're just calculating a mean from a set of sample values, not the whole population. And again, I'm listing these symbols here and what they mean, so you can start getting more familiar with them. And again, here's the same note. We're using x bar here instead of mu, because mu deals with the whole population, but we're just looking at a set of sample values from a population. Okay, so here's our solution. We have x bar is equal to the sum of all of the individual data values here, the sum of x. Remember, sum just means that we're adding the values together. If we're taking a summation of a set of values, we add them together. So here we have 38.5 plus 55.6 plus 22.4 plus 14.1 plus 23.1. We divide it by 5. Now, why do we divide it by 5 here? It's because we have 1, 2, 3, 4, 5 data values in that sample. Okay, and to do this in the correct order, we want to add all of these first because they're sort of implied parentheses right here. And if you remember your rules on PEMDAS, then we need to take care of everything here that would be in these parentheses. So first we add the numerator, then we divide by 5. So that's important. So here we get 153.7 as the summation, then we divide by 5. We get a final answer of 30.74 megabits per second. Okay. Hopefully you did good on that one. Let's go on to talking about the median now. So the median of a data set is the measure of center, that is the middle value when the original data values are arranged in order of increasing or decreasing magnitude. And we'll do an example of this as well. First, some important properties of the median. Number 1, the median does not change by large amounts when we include just a few extreme values. So because of this reason, we can say the median is a resistant measure of center. Now remember this definition of resistant. A statistic is resistant if we can add in some extreme value and if it doesn't impact the data value that we're talking about. And when we do an example, this will make sense too. So the median being the middle value, if we added some value on one extreme or the other, the median will likely not be impacted. So we can say the median is resistant. Number 2. The median does not directly use every data value. So again, these two are somewhat related because if we change the largest value in a data set, the median does not change. Because for example, if the largest value is changed to a much larger value that's on one extreme of the data set, then our middle value will still be what it is. The median will not change. We will do an example of this. Okay, so let's go through a calculation and notation of the median. The median of a sample is sometimes denoted as x tilde or capital M or MED. So you might see median represented in one of these 3 different ways. I think the trickiest one to remember is this x tilde one. So to find the median, first we'll sort the values. So arrange them in order. It can be ascending or descending order, it doesn't matter. Usually it's more natural to list your data values in ascending order, but either way works. So we're going to go through 2 different procedures for finding the median, but this is always the first step. So take your data values and arrange them in order. Now, a way this can differ is if the number of data values is odd, so 3, 5, 7, 9, etc., any odd number, then the median is the number located in the exact middle of the sorted list. So in a way, looking at a data set that has an odd number of data values, it's a little bit easier to find the median. Now, if the number of data values is even, then the median is found by computing the mean of the 2 middle numbers in the sorted list. And we'll do an example of both odd and even. Okay, so here's an example dealing with an odd number of data values. Find the median of the first 5 data speeds here. So 38.5, 55.6, 22.4, 14.1, and 23.1 megabits per second. So here we have 1, 2, 3, 4, 5 data values in this data set. Remember, when we're finding the median, the first thing we do, regardless of the number of data values being odd or even, we first need to sort the data values in order. Okay, so to do this, 14.1 is the lowest number, next 22.4, then 23.1, 38.5, then 55.6. So you need to make sure we have all of our data values here listed in the correct order. Again, it can be ascending or descending order, either one. Next, because there are 5 data values, the number of data values is an odd number, because 5 is an odd number. So the median is the number located exactly in the middle of the sorted list. So in this case, we would cross out 14.1 and 55.6, they're on the outside. Next, we'd cross out 22.4, then 38.5. Then we're left with only 23.1 in the middle. So our correct answer here is 23.1 megabits per second. Now let's do this example with an even number of data values. So here we're going to do something very similar, but now we're going to add in this 6th data point. So what do we do first? First, for finding the median, we always arrange our data values in ascending or descending order. So for example here, we list our numbers, we add in 24.5, so here's our new value here. Now, if we were to try to do what we did for an odd number of data values, we'd cross out 14.1, 55.6, 22.4, 38.5, and then we're left with both of these numbers, so 23.1 and 24.5. So which of these would be our median? Well, actually, neither of those is our median. We still have to take the mean of these two values. Okay, so because there are 6 data values, 6 is an even number. So to find the median here, we compute the mean of the 2 middle numbers. And in this case, the 2 middle numbers are 23.1 and 24.5. And remember how we find the mean here. We sum 23.1 and 24.5. So we add these two together. We divide by the number of data values here, which is 2. So when we add 23.1 plus 24.5, we get 47.6 divided by 2. So for an even number of data values, our median is in between 23.1 and 24.5. In fact, it's the mean of these two numbers. So our final answer here is 23.80 megabits per second. Okay, so make sure that's really clear how to find the median when there's an odd number of data values and how to find the median when there's an even number of data values. For an even number of data values, we actually have to take the mean of 2 values before we can get our final answer. Okay, next we're going to talk about the mode. The mode of a data set is the values that occur with the greatest frequency. Okay, so essentially the data values that we see appear the most often in a data set. We have some important properties of the mode. Number 1, the mode can be found with qualitative data as well as with quantitative data. And remember the difference here. So qualitative data would be colors of shirts, species of gerbils, things like that that don't have a meaningful number to them. Because remember with sports jerseys, those weren't really meaningful numbers. Number 2, a data set can have no mode or one mode or even multiple modes. And we'll talk about an example of all 3 of these cases. And we'll go into this more specifically here. So to find the mode, a data set can have one mode, more than one mode, or no mode. So when 2 data values occur with the same greatest frequency, each one is a mode, and then the data set is said to be bimodal, or having 2 numbers or 2 qualitative measures that appear the most frequently in that data set. And again, we'll do an example. Now the difference here, when we have more than 2 data values that occur with the same frequency, each is a mode, and the data set is said to be multimodal now. So bimodal, where bi means 2, and multimodal, where multi is a number greater than 2. Okay, so we can have a data set that's bimodal, it has 2 modes. We can have a data set that's multimodal, it has more than 2 modes, so it has 3 or more. We can also have no mode. This is when there is no data value that's repeated. So we can say there's no mode at all in the data. Let's do an example here. So let's find the mode in these data values. So we have 0.3, 0.6, 0.3, 0.2, 0.6, 1.2, and 0.3. So to solve for this one, you want to also sort the data values in some way, so organize them a little bit for yourself. The best way to do this is usually also arranging them in ascending or descending order. Usually it's more natural to list numbers in ascending order. So let's take all these data values and list them in ascending order. So here we get 0.2, 0.3, 0.3, 0.3, because there's 1, 2, 3 values of 0.3. Then we have 0.6 and 0.6 because 0.6 shows up twice in our data set. And then we have 1.2. Okay, so first we took all of our data values and we listed them in order. Now we find the mode. So here we identify the data value that appears the most often is 0.3. Okay, so our mode here is 0.3 megabits per second, and here there is only one mode because no other data value also appears 3 times in this data set. So we only have one mode and it's 0.3. Let's do 2 additional examples now. So find the mode of these data values here. First, we want to list them in order. So 0.2, 0.3, 0.3, 0.6, 1.2, 4.0, and 4.0. Now to identify the mode here, this data set has 2 modes, right? Because 0.3 appears 1, 2 times, as well as 4.0 appears 2 times. So this data set has 2 modes. It's considered bimodal, where the final answers here are 0.3 and 4.0 megabits per second. Now the last example here for finding the mode. Let's find the mode from this data set, 0.3, 1.1, 2.4, 4.0, and 5.0. Now you may be able to tell right away, but we'll still arrange these data in order. So 0.3, 1.1, 2.4, 4.0, and 5.0. So here there is no mode because no value is repeated. Okay, so for finding a mode, your data set may have no mode. It may have only one mode. It could have 2 modes where it's considered bimodal, or it could have 3 or more modes where it's considered multimodal. Okay, the next measure of center here is our mid-range. The mid-range of a data set is the measure of center, that is the value midway between the maximum and minimum values in the original data set. Okay, so here you would find the mid-range by first identifying the maximum and the minimum values, and then we'll talk about how to find the midway between. But we would take these 2, add them together, and we divide by 2 to find the midway. Okay, so again, it's stated here, so it's found by adding the maximum data value to the minimum data value, then dividing the sum by 2. Okay, so also this does require us to know the maximum data value and the minimum data value in our data set. Okay, now let's get into some important properties of the mid-range. Now, because the mid-range uses only the maximum and minimum values, it is very sensitive to those extremes. So the mid-range is not a resistant kind of statistic, right? So for mid-range, we're taking the minimum value plus the maximum value dividing by 2. If that maximum value increases by a factor of 10, for example, it might be an outlier, but we still find the mid-range by taking that value and the minimum value and finding what's in between, right? So the mid-range is not considered resistant because it is very sensitive to a value on the extreme, and if those values change, that will definitely impact the mid-range. Now, it's important to know that in practice, the mid-range is rarely used. However, it does have 3 redeeming features. It's relatively easy to compute, right? So we're taking the minimum value plus the maximum value, divide by 2. Next, the mid-range helps reinforce the very important point that there are several different ways to define the center of a data set. Okay, so it depends on those extreme values, but it's likely that the mid-range could reflect a very different measure of center than your mean or your median. Okay, so again, this is telling us that there are definitely several different ways to define the center of a data set. And the mid-range is not that commonly used, but it is pretty easy to calculate. Another point here, the value of the mid-range is sometimes used incorrectly for the median. So we can reduce confusion by clearly defining the mid-range along with the median. And we'll do an example of calculating both the mid-range and the median for a set of data. Okay, it's really important to keep all these equations clear and all these definitions clear. Okay, here for the example, find the mid-range of these Verizon data speeds, and we have them listed here. To find the mid-range, remember we need to find the maximum data value and the minimum data value and sum these together, then divide by 2. So in this data set, our maximum value is 55.6, our minimum data value is 14.1. So we add these 2 together, then we divide by 2. Also really importantly, you have to add these 2 together first, then divide by 2. So we get 34.85 megabits per second as our mid-range value. Now maybe pause it and try to calculate the median for this same set of data. Now to remind you, the median of a data set is the measure of center that is the middle value when the original data values are arranged in order of increasing or decreasing magnitude. Okay, so to find the median, we would take our data set and arrange it in some order. Here for ascending order, we take 14.1, 22.4, 23.1, 38.5, and 55.6. Now for this median, we have 1, 2, 3, 4, 5 data values. So that's an odd number of data values. So to find the median here, it's a little bit easier than if we had a 6th data value that made this an even number. So to find the median, we would take 14.1, 55.6, those cancel out. 38.5, 22.4, those cancel out. Then we're left with just 23.1 in the middle for our median. Now you can already see here the mid-range value, taking the maximum value plus the minimum value, dividing by 2. This value is quite a lot different than the median value. Okay, so once again, it is really important to remember how to solve for each of these definitions and to remember what they really mean. Okay, now we've been doing a lot of examples so far, but now let's talk about how we round off our final answer. So for the mean, median, and mid-range, our final answer will carry one more decimal place than is present in the original set of values. Let's look at an example. So here on the last slide, we just did this example for finding mid-range. The data values we used were 55.6 and 14.1. The maximum and the minimum value here, they both have one number past the decimal place, right? So decimal place 6, decimal place 1. So in our final answer for the mid-range, this final answer carries one more digit past the decimal place than these original values in the data set. So here 55.6 and 14.1, again, both just one digit past the decimal place. Here in our final answer, 0.85, we have 2 digits past the decimal place. Now in this list, you might have noticed that mode is not there. So for the mode, we leave that value as is without rounding. Now this is because values of the mode are the same as some of the original data values. Also importantly here with rounding off, you want to round only your final answer. You don't want to round off intermediate values. For example, here, you wouldn't want to round off 55.6 and 14.1. You want to take this sum, divide by 2, then round off if you need to. Okay, so far in 3.1, we talked a lot about these measures of center. Now let's think critically about whether it's always important to figure out the measures of center for certain sets of data. Now we can always calculate measures of center from a sample of numbers. But again, we want to be critically thinking in statistics, so we should always think about whether it makes sense or not to do so. It's also important to remember chapter 1, what we talked about. So we should also think about the sampling method used to collect the data in the first place. Now, if you remember from chapter 1, we had prepare, analyze, and conclude. Within prepare is sampling method. And I do recommend you going back and refreshing yourself on sampling method. So this is when we ask questions like, were the data collected in a way that is unbiased, or were the data collected in a way that is biased, such as a procedure in which respondents volunteered to participate. Remember, when volunteering is involved, this is an example of a biased sampling method. Okay, so again, sure, we could crunch a lot of numbers, but we need to make sure it's going to be worth it in the end to calculate those different data values and what they truly mean based on the data set. And furthermore, was that data set collected in an unbiased manner? So now let's go through some examples where the mean and median are not meaningful statistics. In other words, calculating the mean or determining the median value would not provide useful statistical information. Our first example here, zip codes of the Gateway Arch in St. Louis, the White House, Air Force Division of the Pentagon, and the Empire State Building, and the Statue of Liberty. Okay, so here we have all these zip codes. These zip codes don't measure or count anything. They're numbers that are just labels for geographic locations. Now, would it really make sense to sum all of these zip codes together, divide by 1, 2, 3, 4, 5, and get a mean? Not really. That mean doesn't really mean anything, right? Another example where it doesn't really make sense to calculate a mean or a median is for ranks of selected national universities, for example. So if the rankings are 2, 3, 7, 10, and 14, these rankings reflect an ordering, but they don't measure or count anything. So would it really make sense to identify the median here in these numbers? Not really, no. And what about the mean? Also likely not useful. Okay, here we're going to get into a little bit more complicated of an example. So we're going to calculate the mean from a frequency distribution. Now, to remind you, on a frequency distribution, we covered this previously. This shows how data are partitioned or grouped among several categories or classes by the listing of categories along with the number or frequency of data values in each category/class. So that example we looked at a lot. Here are different categories or classes. So 1, 2, 3, 4, 5 different classes, where each of the classes specifies the time in seconds for McDonald's lunch drive-through service times, right? So if we had 50 customers total or 50 cars total go through the drive-through, then 11 of those 50 cars, they got through the drive-through between 75 and 124 seconds. 24 of those cars got through the drive-through between 125 and 174 seconds. Okay, now with a table like this, with a frequency distribution table like this, we can calculate a mean, and here's how we do it. So we'll discuss this equation. We're going to first multiply each frequency and class midpoint. So frequency being f, x is the class midpoint. Then we're going to add the products. And we know to do that because this sigma sign here means add. We just covered that a few slides ago. So this sigma symbol means to add everything in parentheses. And then in the denominator, we'll sum all the frequencies. Now, rather than just talking about this equation, let's actually practice using it, okay? Okay, and if you want to follow along, this is table 2.2 from chapter 2 in your textbook. So if we were directed to use the frequency distribution in the first two columns to find the mean, let's see how we would do that. Now, here's some background on this. So when working with data summarized in a frequency distribution, we make calculations possible by pretending that all sample values in each class are equal to the class midpoint. Okay, so why do we need to do that? We know that with a frequency of 11 cars, that they were served between 75 and 124 seconds, but we don't know from this table if 10 of them were served at 78 seconds and then one was served at 123 seconds. We don't know that based on this table. So in order to solve for the mean given a frequency distribution table, we can do so by pretending that all sample values in each class are equal to the class midpoint. Now, to remind you on a class midpoints are the values in the middle of the classes, and they can be found by adding the lower class limit to the upper class limit and dividing that sum by 2. Okay, so you've done this a few times. If you need to stop and practice and do this again, I recommend you doing that. So find the class midpoint for this class, this class, this class, and so on. And remember, to get you started, we would take 75 plus 124, divide that by 2. So now here we have this third column with the class midpoint, or x, in our equation. So we find the class midpoints by taking the lower class limit plus the upper class limit, dividing that sum by 2. So here are all of our class midpoints calculated: 99.5, 149.5, etc. Okay, so when you see a frequency distribution table and you're asked to find the mean, one of the very first things you want to do is calculate the class midpoint. And to calculate the class midpoints, you only need to look at these categories or classes here. And just to remind you again, the class midpoints, these are the values in the middle of the classes. It can be found by adding the lower class limit to the upper class limit, dividing the sum by 2. Okay, so that's what we've done so far. We have this third column. Next, we want to multiply each frequency and class midpoint and then add the products. So you can make a fourth column here. We take each frequency, we multiply that by the class midpoint, or x. So now we can almost ignore this first column here. So we're going to take the frequency 11 multiplied by the class midpoint 99.5, and then we have this data value here. We need to keep doing that for each of our 5 classes. So here's our first class, second class, third class, fourth class, and fifth class. Okay, so once we have each frequency multiplied by each class midpoint, then we want to sum all of these numbers together. Okay, and when we sum all these numbers together, we get 8025.0. Okay, and one thing I didn't mention here yet is that in our equation, we need the summation of all the frequencies. So you can do that at some point too. So we take 11 plus 24 plus 10 plus 3 plus 2. We get the sum of all the frequencies is equal to 50. Okay, so now we have the sum of the products of each frequency multiplied by each class midpoint, right? So we found the class midpoint, we multiplied each frequency by the class midpoint, to get these numbers here. Then we added them all up. We've also summed all the frequencies. So we summed all this, we get a number of 50. Now to remind you of this equation that I showed a couple slides ago, now we can start putting in numbers here. So in this fourth column, what we did was we summed all of the frequencies multiplied by each of the class midpoints. So now in our numerator, we take this value here, it's 8,025. In the denominator now, we take the sum of all the frequencies, so that number there is 50. So overall, to find the mean from a frequency distribution table, we have 8,025 divided by 50, we get an answer of 160.5 seconds. Now, it's important to remember that we didn't know exactly how these frequencies fit into each class, right? So we didn't know that maybe 10 of those people actually got through the drive-thru in 76 seconds. So we had to assume, we had to make an approximation that all 11 of those cars got through the drive-thru at 99.5 seconds. They got through the drive-thru at the class midpoint. Now, because we did that in our calculation, the result of x equal to 160.5 seconds, that's an approximation because it's based on the use of class midpoint values instead of the original list of service times. Okay, so that's a really important thing here for calculating the mean from a frequency distribution table. It's an approximation. Okay, so hopefully so far so good. Next, we're going to talk about a weighted mean. Now, when different x data values are assigned different weights, we can compute a weighted mean. And although we don't use that word average, you may have heard of this concept before when calculating a weighted average. Here it's the same thing, but remember we're calling it a weighted mean. Now here are the symbols that you've seen before, so sigma or the summation. So we're going to sum everything that's in parentheses here. A new symbol here is lowercase w, where lowercase w, this is the different weights. Then in the denominator here, we're going to take the summation of all the weights. Let's do an example with this numerically. So for example, we're going to compute the GPA for a student using this concept of the weighted mean and using the formula for it. So in their first semester, a student took 5 courses. Their final grades, along with the number of credits for each course, were A, that was a 3-credit course, another A for a 4-credit course, B for a 3-credit course, C for a 3-credit course, and finally F in a 1-credit course. So another piece of information we need to know is that the grading system assigns the quality points to letter grades as follows, where an A is equivalent to 4, B 3, C 2, D 1, and F 0. So now let's compute this grade point average, this GPA. One thing I like to do is to organize the data really well. So far what we know is we have the number of credits and the course grade for this student. Right, so we know that in a 3-credit course, that student got an A, in a 4-credit course, that student also got an A, in a 3-credit course, a B, 3-credit course, a C, and a 1-credit course, an F. Now to keep going with this example, we need to figure out the weight, this lowercase w, so how each course is weighted, because that factors into our weighted mean calculation. Now for GPAs, when we have different college courses that are worth different credits. Now it's less impactful for that student because they got an F in a course that's only worth 1 credit. And also it's important that we count this A as the student earned an A in a 4-credit course. Okay, so with a GPA, we think of the number of credits as the weight of that class, as the weight of that course. Now, in order to calculate the weighted mean, we also don't know what A, B, C, and F means until we list the corresponding quality points. Okay, so we were told these in the problem, where an A is worth 4, B is worth 3, C is worth 2, and F is worth 0. Okay, so far for the number of credits, that's the same thing as thinking about the weight of that course. Now for each course grade, this is equivalent to these corresponding quality points. Let's keep going with the example now. So here's our same table, and here's our same equation that we just saw a few slides ago. Now to calculate the weighted mean from this data, looking at this equation, we're going to multiply the weight or the number of credits by x, where x is the corresponding number of quality points. Remember, for example, where an A is worth 4 points. Now let's make sure we understand where all these numbers are coming from in our solution. So here, this course is weighted 3. It's worth 3 credits. that student got an A in a 3-credit course, where an A corresponds to 4 quality points. So here, 3 times 4. Next, we do the same thing. We take the weight. The student also got an A in that course. So we multiply these together. Now we also multiply these together because the student got a B in a 3-credit course, and so on. It is important to see here that we want to multiply here first what's in parentheses, so the weight times each of the quality points that it's worth. So here we multiply 3 times 4 first, that's in parentheses. We also multiply 4 times 4 first, that's in parentheses. Then once we've multiplied all those together, we sum them. Okay, so it's important to see here that 3 times 4 happens first, 4 times 4 happens first, 3 times 3 happens first, and so on. Then we end up adding all these products together. Okay, so here, as the next step says, we add up all these products to obtain the number in the numerator here. Now in the denominator, based on the equation, we need to sum all of the weights. So in the denominator, we need to sum 3, 4, 3, 3, and 1. These are all the number of credits that student took. Okay, so now for order of operations, again, we'd multiply 3 times 4, multiply 4 times 4, etc. We multiply and find the products first. Then we add all the products in the numerator. Then in the denominator, we also sum all of these. Then we take the numerator divided by the denominator. Okay, so we want to do all the operations in the numerator first, then all the operations in the denominator, then we divide the numerator by the denominator. So here, the GPA is 3.07. Okay, so again, here's our last bullet point, divide the numerator by the denominator to get our final answer. The last consideration here is how we round this weighted mean. So the result of the student's GPA is 3.07. Now, according to the round-off rule we just talked about, our final answer can have one more digit past the decimal place than our original values do. In this case, our original values are 3, 4, 3, 3, 1, and 4, 4, 3, 2, 0. So in these original values, there are no digits past the decimal place. So in our final answer, we would think there would be 1 digit past the decimal place. Okay, so if we're abiding by these round-off rules, 3.1 is technically our correct answer. However, it's still important to critically think in statistics, so it's more common to see GPAs with 2 digits past the decimal place. Okay, so although 3.1 is technically correct, according to convention, we do normally see GPAs with 2 digits past the decimal place. So technically, either one of these could be the correct answer here. Okay, that is the end of 3.1. As always, let me know whatever questions you have. I hope you've been keeping up with the homework okay. And as stated on the syllabus, Exam 1 will cover chapters 1, 2, and 3 content coverage. And one thing I mentioned earlier on, the frequency of exams, we have 5 total. We have that number of exams, so you can focus on what's covered in that one exam, get tested over it, then we move on to the next chapters. Okay, again, hope you're staying safe, hope you're staying well. Please feel free to jump into office hours. I'm here over Zoom. Okay, talk to you all soon.